All right, welcome to another video of 1MO3 structure and property of materials. And in this lecture, we'll be talking about crystal structure and lattice structures. So before we talk about that, I want to show you this very beautiful rocks, which is what is called amethyst that I collected. And so this particular rock is made out of this purplish crystal. And you can see the beautiful, each individual crystal have a different crystal orientation. And so when light are reflecting on it, they bounce back in a different way so that you have a different refractive property. Because of that, you see this really shiny property. And by the way, how this is created, this is really interesting. This is essentially quartz crystal. This have the same chemistry as glass that you get from any glassware. So silicon dioxide with a little bit of impurity, making it with this hint of purplish color. And so geologists think that the way these rocks are made in the natural form is that it used to be a piece of lava, and there's some kind of heterogeneity in the lava, and you form this kind of liquid bubble, where the bubble inside a molten glass liquid with silicon dioxide in there. As it cool down, then the crystal will then then the glass or the silicon dioxide will start to solidify into solid. The process of it is very, very slow, and because of that, you have multiple what we call nucleation site. So each of the crystal will grow from one location and another location, and then eventually they bond to they collide to each other, forming this what we call polycrystalline system. And so here, I think there's like hundreds of them, make each individual crystal have a different orientation with same chemistry, same crystal structure, but just different orientation, making this really beautiful structure. I just want to show you that. Okay, so let's go back to the lecture. So in this lecture, we're going to be talking about crystal structure, or we also call it lattice structures. So in this lecture, we're going to be choosing a system where we call what lattice is. So earlier, I showed you those beautiful crystals. Essentially, they are atoms bonded together. And the last lecture, we talked about how when you bond things together, they have different type of bond. They have atomic, ionic, covalent bonds. But we were talking about two atoms bonded together. Well, material made up of much more atoms in trillions or even higher orders. And so how do atoms stack together? They are kind of like Lego blocks. One atom is one unit, and then two atoms bonded together. But then there could be another one, third, fourth, and surrounding, which are called neighboring atoms, that bonded together to form these kind of lattice structure, almost like a truss. And so the nomenclature that we use in material science are called Bravais lattice system. And in total, we have found that the typical Bravais lattice that have what we call translational symmetry, we have 14 type of Bravais lattice. In this course, in the 1MO3 course, we're only going to touch on the surface of this beautiful and yet very in-depth study, which are called crystallography. And in this study, we're going to be talking about only the 4 different type of Bravais lattice system. We're only going to be focusing on the crystal in the cubic system. So we have simple cubic, body center cubic, so body center cubic, face center cubic. And then we also will briefly talk about hexagonal structure, leaving the other type of lattice system for future years. So just want to let you know that this is a very deep topic, and it has a lot of fascinating physics and science coming out from that. But for now, we're just going to be talking about the introduction of that concept. So what is a lattice and what is a unit cell? Well, a crystal consists of many, many unit cells. So for example, here I'm showing you a 2D image of a two-dimensional simple square system, and we can define a unit cell to be a square, let's say. Then here we have a square. And what is cool about this square is that if I just look at this particular square right here, so look at number 1, I have a square with 4 quarter atom inside. This makes it 1 atom. And so what is cool about this is if I look on the right-hand side, let's say we call this the right-hand side the x-axis, and we call the going upward is the y-axis, then we can find that if I just move imagine you have a magnifying glass and move your magnifying glass to the right-hand side, all of a sudden I'm looking at the same thing. So this is called translational symmetry. And in the Bravais lattice system, there's 14 type of lattice all have translational symmetry in the 3-dimensional world. And so here's a 2D system where we have a simple qubit where we can translate onto the right-hand side, and we just look at it and it looks identical, which is beautiful because what it means is we can think of this one unit cell as a building block. We don't need to think of the entirety. We can simplify things and just look at one unit cell, understand the unit cell, understand the property, and then we can just extrapolate from it. Okay? And so a unit cell would be the smallest unit inside this translational symmetry grid. In this case, it's x and y. And what is cool is it can translate in both x and y direction. So here, this one is 4. And how you define a unit cell, usually what we want to do is we want to make sure that the unit cell have the highest symmetry. So in this case, the more appropriate unit cell would be a square. You can potentially define a rectangle, but in this particular case, this rectangle is not the smallest unit possible because a square would be. So that is a redundant system. And then in terms of the diamond, although it's potentially possible to form that kind of unit cell, we tend to prefer to call a unit cell that have a high symmetry. And so in this particular case, we prefer a square system. And so you might ask, where do the atoms sit? I kind of hinted at that already. So to give you an idea, the lattice system is a mathematical system to construct to understand how atoms are arranged together. And each of those lattice point or node, we call motif in the nomenclature. And in each of those motifs, we usually have an atom or at least a molecular group. Okay, so in the simplest case, we'll have one atom inside this node, and we call that motif. And so here we have a 2D simple square system, and we'll call this unit cell. This doesn't actually exist. No material are made like that, but it helps us to understand the nomenclature. So this distance, previously we call R0, which is the atomic separation. In this particular case, R0 is actually equals to A. And so we have a simple square system. A is the lattice parameter. It describes the length or width of the lattice, not necessarily the atom, but the lattice. And so a crystal is created by a lattice grid plus a motif, and the motif could be an atom. So in this case, you might ask, where does the atom sit? Well, it sits in the corner of this particular square unit cell. And so how many atoms are in there? Well, if you look closely, each of these corner atoms, they're not all inside this grid. Only 1/4 of that atom are inside this grid. So, and in one square, we actually share 4 atoms. So 4 corner atoms each have 1/4 of an atom. So in total, we have 1 atom for that particular unit cell. Now, soon you'll find out that atoms are made in 3D, that they're stuck together in 3D network, not 2D. So a corner atom at a 3D unit cell will be 1/8 of a size. Okay. So like we said, here we're going to be talking about crystal system, and we're going to simplify ourselves, and we'll only talk about the metallic system because metallic bonds are less directional and they're easy to understand. And so in metal, there are many types of crystal structures, but the most common type are FCC, BCC, and HCP. And then we also add one which is called a simple cubic. Simple cubic are very hard to find in nature. Materials tend to not like simple cubic, and you'll soon find out why. And it actually makes sense to you if you think about that. A simple cubic cube is not a very structurally stable structure. And so it turns out there's a lot of gap inside this unit cell that making it not very close packed. And close packed is something that making it thermodynamically stable compared to a simple cubic structure. Okay, so let's start off with the simplest concept of just understanding Bravais lattice and understanding a unit cell. And by doing so, we can go into some more realistic materials. So let's start with simple cubic. Simple cubic is the simplest arrangement of atom in 3D, which each corner have 1/8 of an atom. So this corner, for example, this is 1/8 of an atom. And so to draw a unit cell, there's two ways to draw that. The left-hand side diagram is actually the more realistic way of drawing things, where an atom are represented by this ball. And really it's actually an electron cloud with that particular radius, okay? And in this particular case, the X, Y, and Z direction all have a parameter of A. A is the lattice parameter. In this particular case, the atomic radius, sorry about that, atomic radius is R, is half of the lattice parameter. So here we have also A here. So that's the atomic radius. So with that said, how many atoms are there? Well, each of them, we have 8 corners atom, and each one is 1/8. What that means is that we have 8 times 1/8 of an atom, which is equals to 1 atom per unit cell. This is the simplest you can get, and you can think that this cube can just stack in the X, Y, and Z direction, kind of like a Lego block, making a crystal structure. The next one is called the body-centered cubic. And in this particular case, this is the realistic system where structure of iron, tungsten, cobalt, and other type of metal, usually ferrous materials, tend to have this kind of BCC structures. So if you compare to the previous one, which each of the corner have 1/8 of an atom, now what we did is we're going to stuck one more atom inside this cubic, and we're going to stuck it inside this body, and that's why it's called body-centered cubic. And so there's this one extra atom here, this one extra atom. And so this is one atom. And then, so how many atoms are inside this unit cell? We have plus 8 times 1/8, which is equals to 2. Okay, so these are the corner atoms, right? And so a body-centered cubic consists of one body-centered atom plus 8 1/8 of a corner atoms, okay? And so the same thing, commonly we will draw this kind of structure, and now A is representing the new lattice constant, and you can imagine that this actually is no longer R, is no longer 2R. A. This is no longer 2R, because this is R, this is R, and there's a gap there. So A is actually bigger than 2R. And soon you will find out that this is very important, because this helps us to calculate what's the ratio between the atomic radius and the lattice constant, and we can basically get an idea of how packed are these atoms in comparison to a fully dense structure. Right? And by doing that, we can then calculate what is the density. And so here we can also see that, okay, well, this is one unit cell, and then this is another unit cell, and so forth, so on and so forth. And so you can create a structure by stacking these unit cells together, like a Lego block. So this is just summary of what we said. BCC, we have 1/8 of an atom inside each corner, plus one atom in the center, creating 2 atoms per unit cell. Now here I want to show you a video of how a BCC structure looks like. For those that maybe a little bit need help with the corner atoms, how it actually is 1/8. So let's see the corner. So this is a BCC, one corner, involve 1, 2, 3, 4, 6, 5, 6, 7, 8. 8 pieces of corner created 1 atom. And so BCC corner involve 1/8 of an atom. Okay. Hopefully that's clarified why BCC have 2 atoms inside each unit cell. Finally, in the next one, we have what we call the face-centered cubic. And the reason we call it face is instead of stucking one atom into the middle, we now stuck the atom onto the face of each of those ladders. And so we now have a unit where this is A, this is A, and we have we have 1, 2, 3, 4, 5, 6. 6 extra atoms that are half. If you think about that. So these are half atoms. Sorry, let me just erase that. These are half atoms. Now these are 1/8 of an atom. And so how many atoms are inside? Well, we have how many phases? 1, 2, 3, 4, 5, 6. So we have 6 phases. Times 1/2. 1/2. Plus we have 8 corner times 1/8. So this is 1 atom, this is 3 atom, which gives me 4 atoms per unit cell. And turns out FCC is a very common material that are being used in many structures, aluminum, nickel, gold, and so forth. And FCC structure is a very interesting structure because soon we'll find out from the next video that turns out FCC have one of the highest packing factor, making it one of the densest possible structure. And so it makes sense why dense materials such as copper and gold, very heavy metal, tend to have FCC structure as well. And turns out many elements, when they are at the ground state, meaning at the lowest temperature, they prefer to be in this particular closed pack structure. The next one is called the HCP, which is the hexagonal closed pack structure. So it's actually very similar to FCC if we dissect it. But right now, looking at this, hexagonal closed pack is referring to a structure where there is a basal plane, where these atoms stack to each other almost like a hexagon or prism structure. And so here you can see that this is hexagon, structure constructed of 6 different triangles all put together. And they just stack in this A, B, A, B, A, B stacking. This particular crystal structure is also very interesting. Titanium, magnesium, zinc, and zirconium are made of this structure. Magnesium is a very interesting alloy, actually, very interesting metal. And the reason they are interesting is that magnesium are extremely lightweight, but also very, very strong with a drawback, so as zinc is very brittle. And turns out that HCP is a structure where, because it has this close packed plane and then a separation, and that separation from plane to plane, stacking, depending on that separation, you have very different mechanical property, and HCP metal tend to be relatively brittle. Brittle meaning that it requires a lot of force, but not necessarily a lot of deformation to break that materials. So it kind of snap in half. Like imagine a brittle piece of glass. Okay. And so HCP consists of 6 atoms inside unit cell. So here we have free center atoms. And then you can think about how many are there. So this one is a half atom. So this is 2 times 1/2. 1/2. So that makes 1 atom. And then now the rest of it will make 2 atoms. So here we want to show you how it may look like. So imagine here we have 1 atom. Here we have another atom. So this one is 1/6 of an atom. So this is 1/6 of an atom. And how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 12. So that gives me 2 atoms. So in total, we have 3 plus 2 times 1/2 plus 6, 12. Times 1/6, which is equals to 6 atoms per unit cell. So that's HCP. In the next video, we'll talk about how this crystal arrangement have an effect on density, which will be a very interesting topic on Zoom. So thank you.